Hello, everyone. Welcome to our next talk at Chaos West TV. I'm happy to welcome Dan and Thijs from Computest. They are working in the research department at Computest, and they find a couple of CVEs, and they're going to talk about macOS and the security or not of the sandbox there, and how good that's working. Let's see. So the talk is going to last for about 50 minutes, and then we'll do a live Q&A. The talk is also going to be live, so feel free to ask questions on IRC, the standard channel #RC3-CWTV, and on Twitter or Mastodon at the same hashtag but without minus, so RC3-CWTV and 1. And we'll then collect the questions and ask them to the speakers after the talk. We have plenty of time for questions, so feel free to ask questions while the talk is going on. Otherwise, you might forget. If the question is answered, you can, just say that the question has been answered, and we'll not ask it. So yeah, I think that's everything from me. And
shall I take over?
Yeah, sure.
Yeah, cool. All right. Well, welcome and thanks for having us. We would like to talk you through our research that was about the macOS sandbox implementation and TCC, transparency, consent, and control. Let me first introduce ourselves. My name is Dan Keuper. I'm co-presenting today with my colleague Thijs Alkemade, but we're trying to keep our distance due to Corona. So I will do the first part of the presentation, and Thijs will take over for the second part. We work for Computest, and specifically for the research department of Computest, where we do, security research that is not directly affiliated with work for our customers. So we would like to talk to you about the hypothetical situation that you have code execution as an unprivileged user on macOS. And while that's already a pretty good primitive, that's sometimes not enough. You would like to have more privileges, of course. So how exactly do you gain administrative privileges on macOS, and which hurdles do you need to take or overcome in a modern installation of macOS? So the talk is divided into two sections. The first one is a deep dive into the many protection mechanisms that macOS currently has, like code signing, sandboxing, TCC, etc. And then we'll disclose some of the vulnerabilities we have found during our research. Unfortunately, not all vulnerabilities we have mentioned to Apple, or reported to Apple, have been fixed currently. So for some vulnerabilities, we can only give a slight direction of where to look. And we can, of course, share some technical details, but not the vulnerabilities itself. Unfortunately, reporting vulnerabilities to Apple is kind of like a black box. You just send your research notes, and then at some point in the future, you will hear back from them, but there is no a particular timeline for that. So without further ado, let's deep dive into some of the security mechanisms in macOS Big Sur. Starting with Gatekeeper, which is the code signing part of macOS. Code signing was introduced a long time back in macOS Lion, and it's required for almost all applications nowadays. Although you can still run unsigned applications on macOS, but you have to manually accept those as an end user. The code signing verification is handled by a kernel extension called the Apple Mobile File Integrity kernel extension, which is found its origin in the iOS part, hence the word mobile in the kernel extension name. And it also has a user space daemon that work closely together. So a very powerful feature of code signing is something Apple calls entitlements. So basically, every code signed by Apple can be given very fine-grained permissions by Apple. And those are called entitlements, and they typically are given to a very small privileged process. So rather than having a big binary containing all the privilege entitlement that the binary needs, the status quo is that most binaries are split into separate services, where the smaller service has a specific entitlement and also has the relevant entitlement. So this ensures that the attack surface of a binary is as small as possible. This is a very important security mechanism in macOS and used throughout the entire operating system. The cool thing is, though, that once an application has been signed by Apple with a specific entitlement, it has that entitlement for basically ever. So if you are ever in need for a specific entitlement, then what you could do is you could find an older version of an application that had a previous vulnerability which has the entitlement you need, and most often you can just ship that application with your malware, which will give you the same entitlement. So you can see which entitlement a specific binary has. For example, the PS binary needs to get a hold of some process statistics of processes that do not belong to the PS binary itself. For this, it needs a specific entitlement, which is called task for pid allow, which you can see the PS binary holds in macOS. Using the cosine binary of application, you can get some details about who signed the binary, what are the hashes, etc. The signatures of the binary are embedded in the binary itself. There is a specific section at the end of every macOS binary of application, which contains the code signatures of all other sections in the binary. So also the data section, the text section, etc. Everything that is static within the binary is signed. It is also checked on every execution of the application. So whenever you start an application in macOS, the signature of the binary will be verified by the kernel. This can also be true for resources, so like dynamic libraries, but also images or any resource that your application uses, which is included in the app bundle. Those are signed. There is a specific plist in every application, which contains a hash of every resource file, and that is the entire plist is signed, and it's embedded within the application. However, the downside is that those signatures of resource files are only checked on first run and only when the quarantine bit is set. So for example, if you download the application from the internet. There's a good reason this is so, because it would be very time consuming to check all resource for a large application every time you would like to open it. But this also means that as an attacker, you can modify resource files from other applications by just moving the application to a place where you can write, modify resource files, and then the signature will still hold because the resource itself are not checked. Something relatively new and unknown is what is called the hardened runtime. This is enforced for apps from the App Store, but you can also opt in for this if as app developer, if you please, if you don't distribute your apps through the App Store. And the hardened runtime is there to protect applications to various forms of process injection. So it prohibits the use of specific environment variables, which would allow you to override dynamic libraries. It would prevent you from opening writable and executable memory pages, and it will also check the signature of all libraries that you include within the app bundle. We'll come back to hardened runtime in the second part of the presentation. Together with code signing, the sandboxing of application is also a very important part of macOS security nowadays. It was introduced in macOS Leopard a long time ago, and it is enforced for almost all applications. There are very few little applications that don't require sandbox in the base system anymore. In macOS 10.7, this was a little bit rebranded to the word App Sandbox, which mimics the behavior of iOS. Namely that every app now runs within a specific app bundle. So every app will get a specific folder within the library containers folder where it has symlinks to the documents folder, etc., etc. So everything from the app is packed in a single bundle directory. The sandboxing is handled by the kernel extension, the sandbox kernel extension, and it also has a user space daemon, which handles most of the work, because you don't want to do those kinds of things in kernel space, like compiling the sandbox profile, etc. So sandbox profile are written in Scheme, and they can be found on disk in system library sandbox/profiles. The sandbox has hooks in all system calls across the entire kernel tree. It's very fine-grained, very elaborate. And a profile, sandbox profile, is based on the entitlements the application has. So if a specific application has a allow task for bit entitlement, for example, it will get a suitable seatbelt profile to match those entitlements. This is an example profile for the iMessage sandbox. Most sandbox profiles can be found in this directory. So next is the system integrity protection, which was introduced in macOS El Capitan, and is sometimes referred to as rootless, and internally often referred to as CSR, which stands for configurable software restrictions. The goal of a system integrity protection, often called SIP for short, is to limit the power the administrative user has on macOS. And this is because on most macOS installation, there is only a single user, and that user is also the administrator of the installation, which means that as an attacker, if you have code execution, you're often only a single vulnerability or a single password prompt, which the user is most likely to enter, away from having full system access. So with system integrity protection, they wanted to limit the possibilities an attacker has on the system, or basically the power the root user has on the system. What it does, it basically restricts file modifications. It prevents the loading and from kernel extensions or system extensions, since kernel extensions are no longer a real thing in macOS Big Sur. And it also prohibits you from various forms of process injection. So you cannot steal take over a running process that has specific entitlements by disabling process debugging, for example. Here you can see SIP in action. For example, if on a running system you try to remove the bin bash, it will say that the operation is not permitted. You can also not attach a debugger to a system file like binls. That's also blocked. And often you can see if a file is protected or not by looking at the extended attributes of a file. Often you see that they are either restricted or have a specific attribute of COM Apple .rootless, which has no value, but the flag alone makes it so that the system knows that it should protect this file from modification or debugging. Under the hood, system integrity protection is basically just a sandbox profile called platform profile, which is enforced on almost every application. The configuration for this can be found under system library sandbox/rootless.conf. And it's enabled on boot using the CSR active configuration variable, which is stored in NVRAM. So the fact that it's stored in NVRAM makes it so that they can also protect this variable using SIP. So on an active running system, you cannot change the setting of this variable because SIP will actively prohibit you from setting this variable. So if you would like to disable this protection mechanism, you can only do so by booting in an operating system that allows you to write to NVRAM and is not protected by a system integrity protection. So most commonly you do this by booting into the recovery partition, and then you can write this variable, and the next time you boot, the kernel will notice, hey, I should disable SIP, and it will no longer load the relevant profiles. But obviously, even some system files need some privilege access at some point, like the PS binary needs to obtain some information from running processes, and they use entitlements to overcome this. Then we'll move on to transparency, consent, and control, or TCC for short. You have probably seen this if you're a macOS user with the various pop-ups that applications show you when they want to ask you to give access to specific folders or to your camera or location services, etc. It reminds you a little bit about the UIC of Windows Vista. It is relatively new, and it's basically like a dynamic sandbox for private sensitive subsystems. So it's not a sandbox in that the profiles are static, but the user has to give consent before the application can access the specific resource. The permissions for TCC are inherited from the parent process. So, for example, if you give your terminal specific access, then the subprocessor you spawn in the terminal will also have these TCC permissions. And the permissions are stored with the bundle identifier and developer ID of the specific application you give access to, your camera or folder or whatever. This means that, as is the case with the code signing entitlements I talked about earlier, that if you would like to have, as an attacker, would like to have certain TCC permissions, what you could do is you could ship an older vulnerable version of an app that already has camera permissions or other permissions and exploit this older version, and then you will also have that permission. The file location or version or something is not part of the information that is stored about a specific application and their TCC permissions. The TCC subsystem is managed by a specific daemon, TCC daemon. There are at least 2 active daemons running on your system. One will be for the system as a whole, and every specific user will have also have this daemon running under their own account. So your permissions can be different between different users. One use of the system can allow Microsoft Teams to use your camera, while the other user might block this. For this, the system uses an SQLite database, which contains all the permissions. The database itself is protected by system integrity protection. So as an end user, you cannot just manually insert those permissions. Your system integrity protection will prevent that. So you will need to go through the following path to actually add a permission to the TCC database. As suppose TeamViewer would like to access your microphone. How that works is the service that is handling the microphone inputs is Core Audio D, and that will ask TCC for permission for the specific app. TCC will check if the app does have access to microphone permission, and if not, it will forward the request to the notification center. For this, it requires a specific entitlement to do so, and notification center will show you the pop-up with the name of the app and the permission it would like to have. If the user clicks up OK, then the notification center will reply back to the TCC daemon, where the TCC daemon will add it to the SQLite database. Will reply to Core Audio, and Core Audio will give the application access to the microphone or deny it. For this, the TCC daemon has specific entitlements, notably the notification center UI TCC entitlement, which is required for showing the notification center pop-up, and the TCC manager entitlement, which is required to have access to the database. Moving on to the last protection mechanism, the signed system volume. This is a new thing in Big Sur. Since macOS Catalina, you as an end user might have noticed that you now have two volumes on your macOS installation, namely one system volume, which contains all the system files, the macOS base installation. It is mounted read-only and is thus immutable, and a data volume, which is used to store all user data or all files that can be modified at a running system. Under the hood, this is a complex tree of different mount points, or basically symlinks. They are called firm links, and Apple once described it as a bidirectional wormhole in path reversal. Basically, they allow to specifically mount specific point of the data directory within the read-only mount, the read-only system volume. On macOS Catalina, the system volume was mounted read-only and was protected by system integrity protection. But if you could somehow bypass system integrity protection, you could still remount the system volume with read-writable permission, and then you could change system files. With Big Sur, they added an extension to this. And the idea is that it protects the macOS system files from tampering. And it does so by adding a cryptographic signature to all data on the system volume. So it's not only read-only, mounted read-only, it also contains a signature over the entire volume, protecting from tampering. This is done by implementing a Merkle tree of hashes. So every file has a hash which is embedded in the metadata of the file system itself. And on the root node, this is called the seal. So it's a binary tree of hashes. The root also has a hash, and that is called the seal. And the seal is also cryptographically signed. And whenever you boot macOS, it will check if that signature is still valid. If you change any of the files on the system volume, the seal would break, and macOS would refuse to boot because the system integrity can no longer be preserved or guaranteed. For this only works if you have system integrity protection enabled. If you disable system integrity protection, then it will also not use the signed system volume. This makes the question, how is a macOS update installed? Well, currently your system will have a permanently hidden update volume, which is a snapshot of your Big Sur installation. Patches are applied to this snapshot, and if the update succeeds, the snapshot will be sealed, and the system will reboot into the snapshot. If the update fails, it also keeps the previous snapshot with a valid seal, and it can just boot from the old snapshot. You can see that the snapshot is sealed using disk-util. While doing the research about the implementation of this seal, we came across a reproducible kernel crash. So we would like to thank the organizers of this conference for doing this research. So we hope to explore this in the days after this talk. So shortly, overviewing, code signing guarantees that the code was published by a specific organization and hasn't been altered. Seatbelt handles the static permission each app has. TCC handles user controllable permissions. SIP should guarantee the integrity of the system as a whole, so that you cannot change it. And the signed system volume should prevent any modification you do to any of the system files after, so that they won't be available after a reboot. The fact that Apple takes these systems very seriously is reflected in the bug bounties. They pay out for vulnerabilities that bypass the TCC permission check or the sandbox check. The current bug bounties go up to $100,000, which is quite significant, of course. I would like to give the rest of the presentation to my colleague Thijs, who will talk you through some of the vulnerabilities we have found while researching all these permissions.
Okay, we're going to look at a couple of different vulnerabilities we found, and each of them highlights a different aspect of the security measures we saw before. So first of all, Adobe Acrobat. We're going to look at code signing here, specifically the updater part of Adobe Acrobat on macOS. And there's a bit of a problem for certain Macs because they have a main user who doesn't have a standard user account. So for example, it could be that the parent has a admin user account, but the child uses the computer most of the time, and the parent only logs in once every couple of months. Or maybe it's used in a school, or maybe used by elderly people with somebody else managing the machine. And software nowadays really likes to update itself automatically because there may be security vulnerabilities and they get exploited faster and faster. So updating automatically is generally a good thing. However, non-admin users are not allowed to change any files within the applications folder. So this runs into a problem. If there's a normal user logged in, how do you install the update that's now waiting? Well, many applications have found the same solution for this, and that is to have a separate service, which is always running as root, to handle the installation. This is installed as a privileged helper tool. Just like Dan described earlier, it helps separating privileges that you don't really need in the main tool to a separate service which does only one thing, which is installing new updates. How this most of the time works is like this. So the application itself downloads the update, and then it saves a package to a specific directory. And then it connects to the service, and it asks the service, please install this new package. And there are two checks that the service should do. First of all, it should check, is this request really for the application that this tool is a part of? The second check is the package that I should install correctly signed? Packages can also be signed. It's quite similar to how applications can be signed. And if both of these checks fail, then it may be possible to trick the privileged helper tool into installing an invalid update, which means that it is installing something as root, which means that you have privilege escalation. And this actually goes wrong quite often. So the first step, actually the most common way this goes wrong is that there's no signature check at all. There's no check what application is connecting to it. And even if there's a signature check, then we quite often see that it is incorrect. Or maybe it's possible to inject code into the application, into the valid application, and then connect to the privileged helper tool. We'll go more in detail into process injection later. The second step, the most common vulnerability there is a time of check, time of use vulnerability. What this means is that at the time the tool checks the package, it was still valid. But then at the time it installed it, it had been changed. And now it is installing a completely different package than the one it checked. This often happens if you try to install a symlink, which is linked to another location, which can be modified in between checking and using it. So originally, I didn't find this myself. This was Yuobin Sun of Tencent Security Xuan Wu lab. In around May 2020, Adobe published an update that fixed this vulnerability. Yuobin did a great write-up of this vulnerability. At that time, there was no code signing check at all, and it was possible to use a symlink for the update package. I looked at it, I read the report, and then I discovered that it wasn't implemented correctly, but somebody else beat me to it. Cesaba Fitzel of Offensive Security found that the code signing check that Adobe had implemented was incorrect. They used the command line code sign tool instead of the code sign API, which means that there were various ways that you could bypass it. And also for the package, even though they now checked if it was a symlink, it was still possible to hard link the file because they moved the package. The hard links were preserved, which means that you could still change it before it was installed. So a little later after that, I was looking into it and I noticed that they tried to fix it. They tried to implement the code signing check correctly. But even though they added a function to do the correct checking, this function was always returning true. I think it was unfinished. They were probably not ready yet to release that. So the code signing wasn't implemented correctly then either. It was still possible to modify the package. In this case, it was not. They correctly checked that it was a valid normal file, no symlinks, no hard links. But what they didn't check was that it was still possible to have an open file descriptor for that file. So it was possible to open the package, then the application moved it to another location. And then because it was still opened by another application, they could still write to it. So they checked the code signature. After that, it was possible to completely replace the contents with a malicious package. They fixed that in November. I think it's now correctly fixed, but yeah, I'm the third person who has looked at it and still find it vulnerable, so maybe that's wrong too. I recommend you take a look if you want to. But this is not just a vulnerability affecting Adobe. There are many big companies that really should know better that have similar vulnerabilities in the past. So Google Chrome, I think it was not even a year ago, had a vulnerability like this. Microsoft's Auto Updater, Microsoft Teams, which has a separate updater, were also found to be vulnerable like this. And it really is a bigger problem than just having vulnerable software installed, because once you have installed a application with a privileged updater, and you delete the application from your applications folder, then nothing will automatically remove the privileged updater. So if you have ever used Adobe Acrobat in the past and then deleted it, maybe you needed it for one form or something, then you may still have a vulnerable updater running as root, available for all processes on your system with known vulnerabilities. This updater won't update itself. It will only do that if triggered by the application. So I recommend that you check in launch agents or launch daemons directory if there are files there that refer to applications that you have uninstalled, then you really should delete those because they may contain older vulnerable updaters. And next, we're going to look at a vulnerability I found and reported in macOS itself. This is about open and save panels. So these windows are what we are talking about here. If you use macOS, then you probably see those multiple times a day. It's what you use for opening a file or saving a file from an application. You may think them as being very boring security-wise, but in fact, they are very interesting and have some very complicated technology under the hood. Because even in a sandboxed application, if you try to open a file with an open panel, then the open panel shows you all the files you have on disk, even if the application doesn't yet have access to those files. Now, how this magic works is like this. While the window itself is part of the application, the contents of the window are being drawn by a different service. This is again separating services with different permissions in order to restrict the impact of a vulnerability. So this open and save panel service has access to all of the files you have on disk. And once you have selected a file and clicked on the open button, it will give temporary access to that file or that folder to the application so it can open or save that file for a short time. This is part of an internal API. It's known as NS Remote View. And because it's an internal API, it doesn't have official documentation. There's no documentation about it at all. But because it's Objective-C, you can obtain a list of the methods that a class has at runtime by inspecting it. And when I did that for the NS Remote View class, I noticed a very interesting function named snapshot. Now, you may already guess by the name what it does. It takes a screenshot of the contents of the panel and returns it to the application. So the sandboxed application can request a screenshot of what is currently selected in the open panel, which means that you can get an overview of the documents a user has. And for certain files like images, there may even be a preview of that file visible in the screenshot, which is, of course, not something sandboxed applications should not have access to. We have a short demo of that here. Let's see if this works. So first it clicks on open. You'll see that the panel opens. And now we go back to the application and it can grab the contents of the panel. As you can see there, it has obtained a full list of the folders, but it could also call this multiple times to get a really complete overview of the documents the user has if they navigate through it. And I think this vulnerability quite clearly shows that even though this is very interesting attack surface for a sandboxed application, nobody before has looked at it because it's such an obvious vulnerability here that was still there. Luckily, this has now been fixed with macOS Big Sur. It's now no longer allowed for an application to call this function. Next up, we're going to look at another vulnerability. It's also fixed in Big Sur. This was a sandbox escape using system preferences. The macOS sandbox profile allows you to start a new process. On iOS, this is not allowed. The app sandbox won't allow you to start new processes, but on macOS, this is fine. And if you do that, then the application of the command that you start inherits the sandbox configuration of the parent process. So in this case, if you use ls, then you see only the files or folders that you have access to in your sandbox. There's one restriction or one thing that won't work, and that is trying to sandbox or call a sandboxed application within a sandboxed application. If you try to do that, then there will be an error logged and the kernel will terminate the process. So this is, as you can see here, sandbox reinit is forbidden if you try to open Safari, because Safari should be sandboxed. You cannot sandbox and start a new sandbox from a sandbox. Other than that, sandbox violations are not fatal. If you try to read a file that you don't have access to, then you just get an error code. Or if you try to access something, some internal API, that you just get an error. But the application keeps running. So this means that you could try to run a normal application within a sandbox, even though it's not expected to be in a sandbox. I tried it. This with all of the applications included in the system, and most of them failed in some way. There was an error very early on, or they crashed, or they just wouldn't load. There was just one application which was running completely fine, and that was system preferences. I could change all settings that I tried. It was everything about it seemed to be working. This is very odd if you think about it, because system preferences is where you manage your TCC permissions. This is where you approve a kernel extension. So these are the most security sensitive settings that you have on a system. And I could change them in an application that was within my sandbox. Of course, I shouldn't have access to that at all. And when I looked into Activity Monitor and noticed why this was the case, we see here again that it has been separated into multiple services. As you can see here, the security preference pane is a separate service, separate from system preferences itself. And even though system preferences is sandboxed, the security service is not sandboxed. As you can see, there's even another layer there. There's analytics and improvements, and even advertising sections, which are again sandboxed, which are another level separate service. So Apple uses these separate services for their own system preference panes, but you can also install third-party preference panes. So I installed a couple of them here, and these system ones use these XPC services, as I just described, but the older ones are different. They are bundles, which basically means that they are a shared library that can be loaded into a process. And bundles are different from XPC services because they cannot have their own permissions or entitlements. And in this case, there's a service that provides compatibility between the two. So there's a legacy loader XPC service, which can be loaded to load the old style preference pane bundles into system preferences. So this explains why it was working, but it doesn't really give me any control yet over the application. But what I also noticed that if I launched it within my sandbox, it was creating files within the container of my application. As Dan described earlier, the Mac App Sandbox creates a separate container, which means that, for example, the cache directory, which is normally where every application dumps all its files, it's now separated for all different sandbox applications. But because I was launching system preferences in a sandbox, it was also creating those files in the cache directory of my sandbox. This meant that my own application had access to these files, even if, though normally, if you were running system preferences, I would not have access to them. There are 3 files here, and the middle one is very interesting. This is the user cache. This user cache file contains a list of all of the third-party preference panes that you have installed, with their name, icon, and the path to the bundle, so that it doesn't have to read that list every time you launch system preferences. So it can just start a little bit quicker. And what I found was that the path of those bundles is not validated when it uses the cache. So I figured out I could do the following attack. First of all, I start system preferences within my sandbox. I wait for it to create its user cache file with the third-party preference panes I have installed, assuming there's at least one of them. I then kill system preferences, which is allowed because it's a child process of this process. I then modify the cache file to point to a bundle within my application. Then I launch system preferences again, and I wait for the user to activate the preference pane that I modified. We have a demo of that as well. First of all, it will show that the application really is sandboxed by using Activity Monitor. As you can see on the right there, it is sandboxed. It now starts it for the first time, waiting for the cache to be created, which takes a few seconds. Now it starts it for the second time, and now we have to wait for the user to click on run. We open Java. Instead of opening that preference pane, it loads some malicious code, which starts calculator. Now this is, in theory, a sandbox escape, but having this user interaction step is really annoying because it's very unlikely that if system preferences open spontaneously, that the user will click on the preference pane that you want them to. So I looked into ways to automatically open a specific preference pane. And ideally, I would also want to skip the first step. First thing I looked at was that there's a URI scheme for opening a specific preference pane, but this is no longer supported for a third-party preference pane, so this didn't work. But then I noticed that there's also alerts. This is relatively new. If there's, for example, an update pending, then there's this badge on system preferences that you've probably seen. And whenever a new alert is added, the first time system preferences is then started, it will automatically open the preference pane that added that alert, which makes sense because the user is likely opening it, wondering why there's an alert. And this even works for third-party preference panes, even though there's no API, as far as I could tell, for adding that alert. So you could just say this preference pane that has a specific alert, and then it would open that. So this meant I could shorten my attack to the following. First of all, I can create a valid cache file from scratch. This was a bit tricky because it has some timestamps based on modification dates of files. But eventually I figured out how to do that. And then I add an alert for the preference pane I injected. And then I launched system preferences. And this meant that the bundle was automatically started, which meant code execution outside of the sandbox. This is now very fast. You don't even see the system preferences if you immediately terminate it. You can have a demo of that. Again, first validating that it is sandboxed. You really have to pay attention to the doc here, because otherwise you miss that it only bounces once. And we start calculator again. This is something a user might not notice. If your doc is hidden, then this is something you might not see. Or maybe if you leave your computer for a minute, then they could trigger this. And then you have code execution outside of the sandbox. Apple fixed this, and as I said in the Big Sur update, there's a very simple one-line change. If system preferences sees that it is in a sandbox, then it just refuses to start and quits immediately. And I think that's a good thing to do in general. If an application doesn't expect to be sandboxed, then it should refuse to run if it is in a sandbox. Next up, this is not a specific vulnerability that we're going to look at, but it's just a bit of a design issue of TCC in combination with Electron. As Dan said before, the TCC permissions, so for example, storing which applications are allowed to use your camera, are stored based on a bundle identifier, so specific application, and a developer ID, In practice, this is like the code signing identifier. And the path for the application or even the version are irrelevant. So if you download a new copy of an application and you launch it, then it still has the permissions that you gave it. And repeating what Dan said, the check for this only checks the executable. If you have the hardened runtime, then the libraries and frameworks included in that application are also checked when they are loaded. But any other resources within the same application bundle are not checked. In particular, interpreted code is not checked if you have JavaScript files in your application bundle. Electron applications, if you're not familiar with them, they are basically a Chrome instance combined with a web application together into an application which is pretending to be a native application, but is basically just a web application with Chrome. Which means that most of its logic is implemented in JavaScript with a few native libraries to bridge functionality from JavaScript to the native APIs. So what you can do if you have code execution and you want a specific TCC permission, you copy an application that the user has installed to a writable location. You replace the JavaScript files it has with malicious JavaScript code, for example, to steal the webcam images and send them off to a server. You launch the modified application, and then you have access to that TCC permission that the user granted that original application. Now, what TCC permissions might an application have that is using Electron? Well, for some inexplicable reason, applications that want access to your webcam and your microphone really like to use Electron. So all of these, Microsoft Teams, Signal, Slack, Discord, Skype, are all written in Electron, which means they are vulnerable to the same attack. And there really is no good way to protect yourself against this as a user. You can try to revoke the camera permission every time after you use the application, but that's very tedious. Best thing to do is, of course, not to use these applications, but use the web interface if possible. There's one thing you can do, that's keeping track of what applications use your camera, and that's oversight by Objective-C. This gives you a notification if an application tries to use your camera, so you at least know if it tries to access it. But if you are already using the application, then it's very likely that you will not notice that there's now also a malicious copy of that application using that permission. So it's not a full protection, but at least you know that something is using your camera or your microphone. I'm singling out Electron here, but it's really a bigger problem than that, because the hardened runtime is a relatively new addition, which means that for many applications, you can find an older copy somewhere which doesn't have that functionality yet. And then you can just replace any of the libraries that it has with a malicious copy, launch it, and do the same attack. So there's just no way, as far as I know, in TCC to prevent this. And really, it needs some changes by Apple for this functionality to prevent this type of attack. Finally, we're going to look at process injection in general. We already looked at process injection in a couple of places. So for example, if you can inject code into an application, then you can communicate with privileged helper tools that are associated with that application. If you can inject into an application which has TCC permissions, then you can steal those permissions. But what if you can inject into Apple's own apps? What entitlements can you steal, and what can you do with those entitlements? This is about 2 vulnerabilities we reported, but Apple hasn't fixed yet, so we cannot give details about how they work. But we can give a broad overview of how you could exploit this type of vulnerability. So for one of these vulnerabilities, we can sandbox escape. For both of them, we can elevate privilege to root and bypass zip file system restrictions. Sadly, the sandbox escape is quite boring. As long as you can inject code into a non-sandbox process, well, then you can execute code outside the sandbox. We can't give more details about this, but it's a very interesting vulnerability that we maybe can talk about some other time. Privilege escalation is more interesting here. There are a number of applications that are included in a macOS system that have an entitlement like this, the authorization services entitlement. And in particular with these two values, the Apple software and Apple software standard user. What these mean are that this application is allowed to install new packages as long as they are signed by Apple, even without the user approving it. So normally, if to install a new package, you need to enter your password. But this application can install a new package without prompting for the user's password. So for example, it's used for Boot Camp, but there are also other tools like Setup Assistant after setting up a new user account on a new Mac, and install command line tools also has this entitlement. But then we can install an Apple signed package. What can we do with that? Well, luckily, we don't have to search all packages because somebody else already did. Ilias Morvat found that the post-install script of macOS public beta access utility package can execute arbitrary code as root. This is from another blog post from earlier this year, I think. It's a very interesting read, although most bugs that were in that are now fixed. It's still interesting to read it. But this package still works and this attack is still possible. So how it works is like this. The post-install script, so it's a script that's being run after the application is installed. It tries to run a specific command from the disk that you installed it on. But what it doesn't do, it doesn't check that you actually installed on a macOS disk. So if you install on a disk image, which has some older files there, then it will still run that command on that disk with root privileges because the installation is running as root. So this can be used as a normal user application. If you inject into another process, then you can start this installation and then it's running a command as root. And the blog post of Ilias, this was running with access to SIP protected locations because the installer for packages needs to have access to that location. That has been fixed. Apple changed that, so the post-install scripts are now being run by a different command which doesn't have that access. So we need another vulnerability for that. What we found on the macOS Big Sur beta installation disk image was that there is a macOS Update Assistant application which can write to SIP protected locations. So it has a key that says that it can write to all rootless locations, so all file system locations that are protected by SIP. And the heritable here means that it is this permission is also granted to any SIP processes it starts. So using this, you can write to SIP protected locations, which means that you can, for example, also write to the location where the system keeps track of kernel extensions that the user has improved. And if you can then load a malicious or vulnerable kernel extension, then you have kernel code execution. We do have a video demonstrating this, affecting the latest macOS Big Sur. First, again, demonstrating that it is still sandboxed. As you can see here, it will connect to a reverse shell. First, it runs a sandbox escape. Then the privilege escalation is a bit slower because it needs to install the package. Then the SIP bypasses very quickly. And then you can see here we have a reverse shell as root. And just to demonstrate that we can write to SIP protected locations, we go to the system policy configuration directory. This is where kernel extensions that have been approved are being stored. You see the CAX policy file there. As you can see, we created a new file named A here, and that was allowed by the system. So this is just one vulnerability. It can be used to go from sandbox escape to full SIP bypass. Now, first of all, some thoughts about these security measures. Do they actually work, and how good do they work? TCC first. TCC is still pretty new and unknown by developers. If you report a vulnerability related to TCC in a third-party application, then most of the time you still need to explain what TCC is first before they take it seriously. And there needs to be just one application that is vulnerable to process injection or something like that, to allow malware to take the permission and to abuse it, for example, to gain access to your camera. And Electron apps are just inherently vulnerable to this type of attack. So just use the web app if possible. Sandboxing. Now, what we've seen is that sandboxing on iOS receives a lot of attention from security researchers, and the lower level and kernel implementation of this shares a lot of code with macOS. So also in macOS, there's a lot of attention for the security part of the kernel parts of sandboxing. But if you look at more higher layers, so for example, the open panels, then it really seems to be that there's no attention for this at all, because there's simple vulnerabilities like taking screenshots of panels that you don't have access to. So there's a lot of attack surface here that's still unexplored in the sandboxing world of macOS. Finally, process injection. Now, there's probably going to be a question from you about how does this compare to Windows and Linux? Should we all switch to Windows? Is that safer in this regard? Now, I'm much less familiar with Windows and Linux, so take all of this with a grain of salt. I haven't researched that specifically. This is all just a bit of Googling. But as far as I know, there's no real security boundary between different processes as the same user, unless you specifically opt into sandboxing technology for that application. So there's UEP on Windows, there's SE Linux and Docker containers and whatever on Linux. It can be used to restrict access, but that's all opt-in. That's not something that's automatically enforced for applications. So for many legacy applications, they still can access all of the same files, all of the features of your computer, like your webcam, everything that one application can access, every application can access. So in this regard, if you look at this perspective, then TCC really is an extra layer of security that macOS has that is just not comparable to Windows and Linux. If you break TCC, then it's still not less secure than Windows or Linux, because that restriction just does not exist there. However, it's a bit more nuanced than that, because as we've seen here in this presentation, if you have a process injection vulnerability, then, so in particular, if you have a process injection vulnerability allowing you to inject in an application running as the same user, then this can have a huge impact. So on Windows, process injection is just assumed to be there, and everything is designed with that assumption. But on macOS, there are now security assumptions that are based around the idea that process injection is not possible. So we saw that we could inject into macOS applications and then privilege escalate to root and bypass SIP. So it's not a very easy comparison to make to Windows and Linux, because the security measures are just different. Now, finally, to conclude, to answer the question of how secure is this really, Apple is trying to bring the security of macOS to the same level as of iOS. So giving users the ability to control the permissions of applications and the access to sensitive data. But it still has a long way to go, mainly because third-party applications need to protect their applications as well. And Apple could enforce stricter restrictions on other applications, but they really don't want to enforce too many new restrictions all at once, because they really need third-party developers on their system. Apple could lock down their system completely, allow only App Store apps, but they don't want to do that currently. That's why we're in this situation at the moment. And that's also why macOS is still not on the same level as iOS. Thank you very much for listening. I hope this was interesting for you. And let's hear some questions.
Great. Thanks a lot for your talk. There was a lot of information in there.
Definitely.
I learned a lot. So we actually do have quite a few questions, ranging from the technical to the not so technical.
Okay.
I'll maybe start with a not so technical question to compensate for the technicality of the talk. So someone asked whether Apple actually paid you out for some of the exploits that you uncovered, or if you can say that, that'd be great.
So for many of the vulnerabilities we have reported, those are not fixed, so there is also no bounty amount being specified at this moment. Some of the vulnerabilities are fixed, and a bounty was awarded, but we're not going to comment on the amount of bounty paid for that. Sorry.
It's totally understandable. It's just, I guess, something that people find interesting to get some real understanding of.
Yeah.
Things that they don't have personal experience of. It's not like you report one every day. Great. And then one of the earliest questions I've got, maybe I'll start from the beginning. Someone asked how does the terminal inherit all file access rights to all the tools launched from it?
Yeah, that's a good question. We did some investigation in that. I'm not entirely sure how that works. That still requires some research, I think.
So if you use terminal, then it doesn't have... you still get a prompt for giving it access to your documents or access to your desktop.
Yeah.
And there's certain locations that you can't read from your terminal. So I don't think terminal is exceptional in that regard.
No, but if you start a tool from the terminal,
then it will have the permissions of terminal.
Yeah, it will have the permissions of its parent, which is the terminal. So you can, like Vim, inside the documents folder once you give the terminal permission, while Vim is a separate process. Yeah, there is something with a ticketing system. I think that's something I saw in the XPC messages going back and forth from TCC. But I'm not entirely sure how that works under the hood, actually. I'm not sure if you found the very specific details, but...
I think there's always some kind of parent process which determines the TCC permissions that a tree of processes has.
Yeah.
It has some logic to resolve that.
Yeah.
Not entirely sure how it works for all processes. In general, it's just the application in your doc that it's running inside.
Cool. Probably a good idea not to use super user privileges, but I mean, that's...
You see a lot of people who say just give full disk access to terminal, but it's also not a good idea because many applications can just write to a file that you will execute in terminal, and then it has full disk access.
Yeah.
So it's not enough to just not use super user. You also have to watch out with other permissions.
Exactly.
Yeah, definitely. Yeah.
Because the super user thing is one thing that everyone knows, but there's more to it.
The powers of the system, the super user, is limited on modern macOS because they're leaning more towards sandboxing and the TCC permissions and system integrity protection, where the super user becomes less powerful.
Interesting. Okay. And then the next question was, what is required to restore full dtrace access to everything on Big Sur?
I think you will need to, well, at least you need to disable system integrity protection, which you can do from the recovery partition. I think that should be enough, but it could be that they crippled dtrace in the Big Sur release as well. I haven't seen that, actually.
I haven't tried it with dtrace, but I know that you can disable certain parts of SIP to still be allowed to attach debuggers to arbitrary system services.
Yeah.
So it's probably just disable SIP.
Cool. By the way, I mean, if you want to come back on some questions that I asked, type in the chat and I'll try to ask them back, because that's something that's missing if I ask the questions and not necessarily know the intention of the person asking. The next question was, why didn't Adobe use a Mac or Unix domain socket service. MACH. Did I?
Because then you will need to have the service running at all time, I think.
Yeah, that wouldn't really solve the vulnerability itself, which is that you can trigger it to install a package.
No.
The communication is happening using XPC, which is convenient because then the daemon is started when it's needed.
Yeah. But the vulnerability works regardless of that.
Yes.
I would actually hope that there would be one update framework that every app would use, which was secure by default or something, because now every system has at least 5 helper tools and even 5 legacy helper tools of applications that you already have this removed. So now we are in this situation where your macOS installation is full of helper tools with all with the same problems for some reason, because this is hard thing to do. So yeah, the problem is with the application receiving it's what the application, the helper tool itself does, not on the communication channel.
The next question already, which was, why isn't there one true way to implement safe updates?
Well,
I guess
you have the App Store, of course. That's the one true way, secure way of distributing apps. But if you publish your app in the App Store, well, there are other problems you might encounter, like certain sandbox profile that just doesn't work for your app. But if you
paying the Apple tax,
the Apple tax, obviously, yeah. So the App Store is the obvious way. But somehow, yeah, if you don't go through the App Store, then every application thinks they have to reinvent the wheel and write their own updater, which, I think that's the reason.
Yeah, I mean, that was also then the next question. You seem to be almost of one mind. The person then asked, does Apple subject its own... No, sorry. Is there an auto updater for third-party applications on macOS except the App Store with its 30% tax? And I think you just...
Yeah, I don't think so. You used to have, how was it called? The framework for...
There's Sparkle.
Sparkle?
Which is a third-party framework that you can use to update your own applications.
Yeah.
But as far as I know, I haven't looked at it in a while, it doesn't have support for a privileged updater. So it would prompt you for an admin password if you try to update it as a normal user.
All right.
I think if we can send a robot to Mars, then we can have safe updates, but that's apparently very difficult. Different problem.
And the last question in this thread is, I think, does Apple subject its own applications to the same restrictions, or are some of Apple's own applications privileged? And does Apple pay its own 30% tax, which...
I think, do they mean applications from Apple that are distributed through the App Store?
The question doesn't specify, so maybe...
But I think, so of course, for the system files itself, there are many apps which have special permissions, like PS is the most easy example I can think of. But also the apps that are distributed through the App Store will probably have specific permissions that other apps don't have. And it might not be the case for things like iMovie or so, but the Big Sur installer has special permissions, and it also requires special permissions in order to install. And it is distributed through the App Store. So I think that...
Apple uses a lot of its own permissions that it won't give to other developers.
Yep.
That's also part of how the system works.
Yep.
Many entitlements are just for communicating with other services. Then that's just not an entitlement that another application can ever get.
Yep.
Now we've got a different type of question. So is there a way to toggle privileges or access rights of applications by using automation? So can you revoke rights to camera per script?
Well, as you saw, the TCC database is protected by SIP.
Yep.
So if you want to give a tool access to it, then you would need to find a way around that. And this means that there really is no way to easily automate that.
No, well, there is one way. The system TCC database is protected by SIP, and you cannot write to it unless you disable zip. The user TCC file is, you can modify it. It is protected by zip, but you can modify it if the application has full disk access. Then you can write directly to the database. If that directly solves your problem, I'm not entirely sure. I'm not sure if the daemon will directly pick up on any changes you manually do to the database. I'm not entirely sure. It can very well be that those are cached within the memory space of the daemon.
You can kill TCC daemon and it will automatically restart.
Yeah,
that works.
Sounds like a tedious solution, but yeah, you could do something like that with a special helper tool you write yourself to revoke access, and then just kicking the TCC daemon. So you can revoke the camera permission for Microsoft Teams at the end of every day of your working day. That is something you could do.
Yeah, I think it's very interesting that Apple has not implemented a way for permission to be granted for a short time. So you can just say, give access to the camera for the next hour or so.
Yeah, but maybe they will in the on iOS. You can now say I want only. The application should only have access to specific photos, or it can only use my location once. It could be, of course, that this will also be found a way to macOS, and that you can grant permissions for a short period of time. Yeah.
Ask Apple. I don't know how responsive they are to those sorts of suggestions, but I mean,
yeah.
User voice is something I think Microsoft uses that quite a lot. Now we've got another question, which is, how does Apple Sandboxing compare to FreeBSD, Linux, Capsicum, and Cloudabee?
I'm not particularly familiar with the last one, but I think it's pretty similar to the first one, Secomp. It just limits basically all system calls you can imagine. Yeah, I think it's very similar to that, but I'm not an expert on the Linux sandbox as of currently, so I could be mistaken here. But as to my understanding, it's pretty similar. Yeah. Only that, yeah, the difference, of course, is that with macOS, it's mandatory for almost all apps, whereas on Linux, it's most often still an opt-in feature, where your distribution will most likely sandbox many of your default system applications, so that if a vulnerability is found within one of those system files, system binaries, you cannot directly leverage from the privilege escalation or so. Where on macOS, this just, you cannot turn it off, or it's just part of the system as a whole, I think. So, but also here, I'm not an expert on the current state of Linux sandboxing.
Right. So we did get, someone said thank you for the questions, for the answers. So they seem to be enjoying your type of answering. That's very encouraging.
Cool.
We have a new question from someone who hasn't asked the question yet. That's, are the standard desktop container formats, Snap on Ubuntu, Flatpak, and App Image comparable to that? I think it's a follow-up, maybe.
I also don't know anything about those.
Nope. Well, I think Snap is like a container, so it's quite similar to, I think that uses the use space containers. But I'm also not an expert on this. Sorry. No.
Okay.
I can answer the question, but then I'm just guessing. So,
well, so maybe we can come back to that later. And then I think there was another follow-up on the question earlier about the Mac age. Is it Mac age? How do you pronounce it? M-A-C-H?
M-A-C-H. Oh, Mac.
Mac? Because it was the question, why didn't Adobe use a Mac or Unix domain socket service?
Well,
that was the question earlier. I'm just referring to that question because I've never seen Mac age, M-A-C-H.
Yeah,
anyway,
Mac,
so the follow-up.
The old interpersonal communication tool that was used within macOS, but it has been replaced with XPC, which I think is a layer on top of Mac messages. but currently
Okay.
everything is XPC.
So the follow-up was the updater could read. So I think it's an idea, a proposal of
Okay.
something that could work. So I'll try to
Yeah.
explain it. The updater could read a signed update from a past file descriptor. Mac IPC and Unix domain sockets allow file descriptor passing, and launchd can be used to build a service with socket activation. So the socket Mac port can be bound by launchd, and it spawns the update service just like inetd used to spawn HTTPD, FTPD.
Okay.
I think that could work in theory, but you would have to.
Then you still have to copy the updates to the folder. You have to check the signature. I can imagine that it will help in some way if the file descriptor, you already opened the file descriptor and passed that along. At some part of the solution, but I think there are just too many things that can go wrong after you have the file descriptor. You still have to copy it. You still have to validate its signature. It would definitely help if you get a open file descriptor which you can work on. That would solve part of the problem. It might even be that this is possible with XPC, but I'm not entirely sure if that's possible. When I think about it, I don't think that is actually, no.
Yeah, but that's easier than copying a file.
Yes. Yeah, correct. So I think we'll operate there of writing a secure updater. And we only have to convince all the application suppliers of using it, and then we're done.
Otherwise, you have a time of check versus time of use exploit.
Yeah. No.
Okay. Great. I think that was actually I think I've mentioned all questions. If I haven't, do post it quickly. So thank you very much for this very interesting talk.
Yeah.
I know I've learned how to say Mac. It's Mac. Okay, Mac. Just Mac. Okay. Right. So thank you for your first talk at C3. I'm sure you'll be welcome again in the future with more developments and more research. So this is it on Chaos West TV for the next hour and a half. I think the next talk has been postponed.